Hello, good morning. How's everyone doing today?
Doing good. How are you doing today?
Good, thank you. All right, so today we were working on lab 8, number 8. It's called Rotational Dynamics. For this lab, we are quite ahead of our lectures. So I know everybody has a slightly different pace in their lectures, but overall, I don't think we have gone quite far into rotational dynamics in all of our lectures. So we'll spend some time and do some catching up with the concepts, and we'll be able to do our lab. So to start with, let's introduce an idea of something called a rotational inertia of an object. Okay, we're all familiar with the word inertia, right? So historically, inertia is a word that's been described in the feature of an object tendency to stay in motion unless it's being acted upon by an external force. Nowadays, we know, well, that's just Newton's first law, right? But historically, there is a word inertia that's been left. And it's really just describing the mass, because if you look at Newton's second law, F equals ma. So what does that tell you? That tells you to change the status of motion of an object. In other words, to give an object an acceleration. The bigger the mass, the harder it is, right? The bigger the mass, the bigger the force it requires. So inertia sort of tell you how hard it is, or mass tells you how hard it is to change the acceleration, or to give it an acceleration, the bigger of a force they require. So rotational inertia is equivalent of that idea in rotation. So just like how hard it is to change the motion of the object in translation, this is to tell you how hard it is to change the motion of the object in rotation. So what it gives a rotational acceleration, how hard it is to give it a rotational acceleration. So you can see that, well, when you just swing around this little mass with radius r, sort of just swing it across with a radius r, and it's attached to a rope, both of the mass and radius will make a difference, right? So when you are swinging around a bigger mass, do you think it's hard to rotate? A bigger mass versus a smaller mass, which one is harder?
Bigger.
The bigger mass, very good. Now, if you use a longer string versus a shorter string, which one is harder to rotate?
The shorter string?
And like, think about if it's really long and then you have to keep it level.
The longer string.
The longer string, yes. So both of the mass and the radius will affect how hard it is to rotate it. And both of them will affect your rotational inertia. So we define rotational inertia of an object is the mass of an object times the radius squared. Radius is how far you wanted to rotate it around which circle, right? So that's the radius of the circle that you want to rotate. So mr squared is the equation. You have a bunch of those masses, then you need to add them all up, right? So m1 r1 squared plus m2 r2 squared, and m3 r3 if you have 3 masses, and so on and so on. If you have a continuous mass distribution, we know that little m's becomes dm, and instead of a summation, you do a integration. So that is how you will calculate rotational inertia in different scenarios. When you have, well, I'm going to show you 2 objects. Okay, one of the disk, that is the one that we are doing in our lab. But first, let's start out with the ring. The ring is easier to understand. For a ring, you can see that here I have one mass. Imagine if I have another mass with the radius r, right? the rotational inertia is mr squared plus mr squared. So it's 2mr squared if I have 2. If I have 3, I add another one. If I have 3 of them. If I have 4, I add another one. So if I have a lot of masses, they're all having the same radius away from the center, is as if I'm adding all of the masses together and they all have the same radius. So a ring is just like that. You can view that ring as a integration of many small masses. And they're all at the same radius away from the center. So for a ring, the rotational inertia relative to its center is the mass of the ring times radius squared of the ring, because all of its little masses are all at the same radius. So when you add them up, is the total mass of the ring. So for the ring, you can see we use this equation. But for a disk, we will have to change the equation. You can see for the disk, do you think with the same mass m, do you think it's now easier to rotate a disk, or is it easier to rotate a ring? For the disk, some of the masses are at radius r away from the center, but a lot of the masses are much closer because it's now that hollow is now being filled with some of the masses. So you can see that the overall, it is actually easier to rotate a disk if it's the same mass as your ring. The rotational inertia for a disk is 1/2 m times r squared. In your lecture, you will see this later, and we will probably talk about exactly where the 1/2 come from. But here, we will try to make sense that, well, it is 1/2 because it makes sense for it to be smaller than the ring, because some of the masses are actually closer to the center, making it easier to rotate. So in our lab, we are trying to rotate an object of 3 different disks. So they're all of the same different shape. Some of them are much longer and thinner. Some of them are much shorter and more flat. So here, this is a wheel. You have 3 different cylinders, 3 different disks, right? Disk 1, disk 2, and disk 3. And part B of this lab is to calculate the rotational inertia using the definition we just talked about. For rotational inertia for a disk is simply 1/2 mr squared. Now you have 3 different disks. So the entire rotational inertia is disk 1 plus disk 2 plus the disk 3 of them added together. We actually talk about part B first, the theory part, before we do the part. Okay, so this is the equation of how you calculate it in theory. And this is essentially the same as the pre-lab we did. So let's look at our pre-lab, and then we can go back to the slides here. Our pre-lab has 4 different disks, but it's nothing different than calculating 3. So instead of adding 3 together, you add 4 together. Each of them is a disk, so use 1/2 mr squared equation for that particular shape. That's a disk shape, right? So I1 is 1/2 m1 r1 squared. I2 is 1/2 m2 r2 squared, and so on for 3 and 4, so on and so forth. Now, the one little extra process is that we are not given the individual masses. What we are given is the total mass of the wheel. Because you cannot take this apart, you cannot chop it off and measure them separately. You only know how much the mass is overall. And you can measure the dimensions of how much the radius and the length by using your, by doing some length measurement. But you don't really know the individual masses. So what do? That's one extra step, is to substitute the mass with something else that you know. So we do know the total mass, and we can calculate the volume for each of them. So what is, so they're all made of the same material, so they all have the same density, right? What is density? Do you still remember and recall how density is related to mass? How do we get mass if we have mass, how do we get density of an object? You can also feel free to type in the chat if you like. Density would be mass divided by what? What quantity? Volume, thank you very much. Thank you. Yes, very good. Melina and Nicholas, mass divided by volume is the density. So you can see that, well, mass 1 is the density times volume 1. So this V means volume, not velocity. Okay, so this is volume. They're all of the same density. Mass 2 is the same density volume 2 because they're all made of the same materials. So I have the mass for all of them. In terms of its density, is the total mass. Well, I don't know the individual masses, but I know the total mass. So capital M over capital V, V total volume. Okay, so total volume is V1 plus V2 plus V3 plus V4, all of the volume added together. So this times V1 is mass 1. This will be the same density times volume 2. This will be the same density times volume 3. This will be the same density times volume 4. Okay, and now you can calculate its individual volumes by using the area times the length. So for a cylinder, right, or for a disc shape, the volume is pi r squared times L. So L is the height or the length, R is the radius, right? So that's the formula we use for finding the volume. And for each of the wheel, the radius is given, length is given. So I can do V1, V2, V3, V4. I can calculate all my volumes so that you can calculate individual masses. And then you can plug into the rotational inertia equation and you can calculate the rotational inertia. Okay. So in our lab, we are dealing with only 3 disks, so that's even more simplified. So you can see that I is I1 plus I2 plus I3, right? Each of them is M1 R1 squared plus M2 R2 squared plus M3 R3 squared. And I simply substitute the M with volume. So the M1 is overall mass, right? Divided by the overall volume. So R1 squared times V1 squared times V1 R1 squared. So 1/2 the same density, V2 R2 squared, and again the same density times V3 R3 squared. So this is the equation that you were looking at. This is where it comes from. So purely come from our definition of what the rotational inertia for a disk. So in our lab, we will look at the measurement for R's and we will measurement for the length and we can calculate it. So any questions about this particular theory part? So for part B, any questions? If you want to say it or if you want to type it, it's all okay. Any questions so far? All good? Let's take a quick look at part B. So we will actually look at we will actually look at our part B first before we do part A. I'm not sure if I shared Were you able to see my video screen?
Yes, we can see it.
Okay, actually it's on my, yeah, now, okay. So I was sharing my desk, the windows, but now it's the Chrome. So let's switch to part B. Where is part B? It's actually to the very end. Sorry, that happened real quick. Length dimensions. 15.61, that's in millimeters. That is your measurement for L2. Okay, that's the height of the disc in the middle. That's your height too. 51.71 millimeters, that is L3. 51.81 millimeters, that's your L1. So you get the length for all of them?
With
30.26 millimeters. Can anybody tell me what is that measuring? What is that quantity? The 30.26 millimeters. What is that?
Is it the radius?
Yeah, that is giving us the radius, but take a look at how they got it. They cannot really stop halfway, right? So they have to measure directly across that third cylinder. So give us a diameter of the third wheel. So that's diameter of wheel 3. So you divide 30.26 by 2. That will be your R3. That's your R3.
With these dimensions, that concludes the rotational dynamics.
Okay, so just see what they did. They did a measurement, and R1 is the same as R3. But then now let's look at R2. So now they measured something, and you can read from the video 85.4. 85.4, is that the radius of the second wheel? Is that R2? Or do we need to do something to it before we can write down what R2 is? What is R2? Let's look at how they measure that 85. So this give us
that concludes the rotational
85.4. So how do we get R2?
We have to add the 85.4 to the radius of R1.
Perfect. Thank you so much. That's excellent. You can see you cannot really get to the center of the second wheel, so you need to add the radius of your third wheel, which is 15.13 millimeters onto 85, and that's your radius too. Excellent. All right, so you can see how they have do the length measurement, and you can calculate your rotational inertia theoretically. And now the second part, the part A, is to finding your rotational inertia experimentally. Okay, so this one has a little bit more concept into it, and we haven't learned it, but that's okay. We will go over this together. So like Newton's second law, okay, first of all, let's review what Newton's second law is well, just like how force give you an acceleration, now instead of a acceleration, linear acceleration, you have an angular acceleration, because instead of moving translationally, you are now moving rotation. In a rotation, you're rotating. If you apply Newton's second law to this mass, so what we are making this rotate is to hang a string with the mass hanging onto the wheel. So as the mass moving down, the string unravels and the wheel rotates. Okay, so that's how we rotate it. If you're looking at Newton's second law on the mass, on this guy, there are two forces acting on it. The gravity pointing down and the tension pointing up, okay? So if we're saying, well, let's set the forces equal to mass times the acceleration of the hanging mass, you can say tension is m times g minus a. So that's just Newton's second law. That part is old. That part is knowledge we already know. But to relate that to the rotation of the wheel, that is a part we haven't talked about yet. So let's go through that part again. You can see that there is a relationship between how fast the mass acceleration, linear acceleration down versus how fast the wheel rotates. They are connected. Why? Because they are connected by the strain, right? So you can see that if the strain goes down for a total distance of a few inches, and that means it has been unraveled from the wheel for that many inches. And that is corresponding to how many revolutions the wheel has been rotating. So there is a relationship between the linear acceleration of the mass and the angular acceleration of the wheel. They're simply related by the radius r. Okay, so this is very similar to what we talked about. The linear acceleration, linear velocity is related to angular velocity times radius r, right? Because if you talk about angular velocity, you will say, oh, 2 pi radians per second. But if you talk about the linear velocity, you say 2 pi r per second. 2 pi r might be, you say, oh, how many centimeters? It counts how many centimeters per second. Here you say how many revolutions per second. So that is very similar to that relationship. This one we have seen in our class, I believe. So the acceleration, an angular acceleration of A is related to the linear angular acceleration of the wheel by simply multiplied by radius r. So the reason we write this using angular acceleration is because what we measure with our photo gate, what you read on your computer, is alpha, okay? So you're going to replace A with alpha r. So this part is still something we got from Newton's second law directly, right? But you can see that the goal is to measure rotational inertia. So we're saying, okay, in order to have an acceleration, you need a force. Here we have a very sort of a counterpart for rotation is that in order to have angular acceleration, you need to have a torque, okay? So that's exactly like how we had Newton's second law. So force becomes torque, A becomes alpha, and mass becomes I. So I sort of tells you how hard it is to rotate this thing, just like how hard it is to accelerate some object. So torque equals I alpha is what we call Newton's second law for rotation, okay? So you can see that, well, in order to measure I experimentally, you measure this alpha. We know that our machine or software could measure the alpha using the sensors. If we can also get our torque, then the slope will be our I. So we can get our torque by using the definitions of a torque is that's the force times the level arm, the radius r. So how you generate a bigger torque, I believe you all have the experience of trying to generate a bigger torque. For example, when you try to open the door, do you want to push it at the doorknob, or do you want to push it really close to the hinge? When you try to open the door, where would you push the door? You push it further.
By the doorknob?
Yeah, by the doorknob, where it is as far as possible from the hinge. Hinge where it starts rotating. So you can see if you push your force close to the hinge, you have a very small level arm and you have a very small torque. No matter how big your force is, you're still generating a small torque, which is hard to generate a big angular acceleration, right? So like also when you're trying to loosen a bolt, you use your you'll try to have a long ever arm, you try to hold it further away from where you try to loosen, right? So you give yourself a bigger L, bigger level arm, and then generate a bigger torque. So torque depends on force and the radius r. So here, your force is a tension because that is what is dragging the small wheel and making it rotate. This is your force. And it's rotating relative to the center of this axis that you can't see, but let's draw a dashed line to show. So from the center to where the force is applied, this is the level arm. R3 is your level arm, okay? So to calculate this torque, use the tension you just calculated, multiply by the radius R, that's R3, and you can get all the torques. So in our lab, what we will do is we add different masses. So you can see each time it will give you a different angular acceleration. We measure that. We will record these using the photo gauge, and we plug in this number, and this R is R3, okay? And the radius, you can get the torque. So if you plot everything, you will get a graph where the slope show you the rotational inertia, and that's your experimental value. You can compare your experimental value with the theoretical value you calculated using formulas to see if they agree or not. You can see that it will not pass through 0, 0. So if you plot this, it's not going to pass through the origin. It will have a y-intercept, okay? So the y-intercept is all, so a lot of times in our lab is because it will always have some friction. So it's the torque due to that friction. So that will also show up in your graph. So let's take a look at our video to see how do we record these different data. So A1 to A9, and they did something for fun. They did do A10 in the video. So step 10, you do not use that. You can ignore A10 step because that is when you're wrapping everything around the bigger wheel. But we are doing simply wrapping it around the smaller wheel. We're not going to do the big wheel. So that you can just ignore. Let's go to part A. Wrap around the small wheel to see what the data looks like. Okay, so the first mass, also the data sheet is listed in the order that the experiment is done. Okay, so the first mass is 150 grams. You will write 150 grams under the added mass. But we use kilograms, we use SI unit. So instead of that, you will write 0.15 kilograms. And for that mass, you added what is the acceleration? You get it from the slope of your data, and they will show you the slope here. So the slope 0.71 is your angular acceleration for this mass. Okay, so write that down in your first row. You can calculate your torque later. And then they will use a different mass now. They will just continue to add different masses and record different slopes. So here you do 0.55 kilograms. That's the second data point you're going to take. So 4.26 will be your second angular acceleration. So you will continue to do this for all of these different masses. Eventually they did one for fun. So that is 0.65 kilograms, and then you will also get your slope for that. And eventually they did something when you don't hand mass at all. So let's see. Part A10 you ignore, okay? So we don't do any of that. Ignore all of that. And we continue at part 11. You don't put any weight on it. don't put any weight on it. How do you get it to spin? You'll have to spin it yourself, right? So you give it a spin. So does this velocity make sense? Take a look at velocity. So the velocity, the sensor, so the velocity is when you have these little long sheet passing by the sensor, it records a velocity. So it passing by it multiple times and you record multiple velocity. So if you look at the velocity is 13.4, 13.1, 13.1, 13.0, it doesn't change much at all. Does this make sense to you? Is that what you would expect? Anyone? Do you think that makes sense? That velocity doesn't change much? Yes, Brandon said yes. And why would not change much? Yeah, because now you have a uniform circular motion. Excellent. Now you don't have much of an acceleration because nothing is weighing it down. It just have that free spin. So you should have pretty much constant uniform velocity. So that makes sense. And but you see that it still has a little bit friction. So it does slow down a little bit. And this will give us an idea of that friction. Okay? When you plot it, you can see that it's fairly flat, but slowly declining because it still have that friction. So the last row on your data sheet, you write 0 for added mass because we didn't add any masses, and then there's 0 torque. But you still have an angular acceleration that is due to friction, and you'll write negative 0.45 for your alpha for the last row. So that gives you a one extra data point for what it is when you, what does the friction looks like when you have no added mass. So after that, you will write, you will plot all the data, and let's go back to our data sheet. So in this case, change everything to make sure that you use kilograms here, and A is already in this radius. You don't have to do anything, radians per second square. And alpha, the R that was in millimeters from your data, change it to meters. So if you do that, your slope should be in this correct unit. And that is your experimental value for I. Okay, and your y-intercept will be your friction. Okay, so you compare this I to the I you calculated theoretically, and that will concludes this lab. Okay, so that's all for this lab. I do want to point out, so if you do go ahead and go back to watch the video, you might notice they did say there was a small error in this data. But I'm asking you guys to ignore it because okay, so they did, what they were doing is they did not try to measure alpha directly. Okay, so they were trying to measure A, the linear velocity. So to get the linear velocity, they need to tell the computer the circumference, because computer doesn't really care about whether it's a linear or alpha. It simply tells you how many units per second, whether the velocity is in centimeters per second or radius per second. The computer doesn't care. So what their intention was for the computer to measure A, and you have to divide that slope, divide by the radius R to get alpha. But it's more straightforward if you simply tell the computer this unit I'm entering is radians, and your slope will automatically already be in radians per second square. So that's already alpha, and you don't have to divide by R. So if we were to do this in person, I will tell you guys, measure alpha directly by tell your computer that the 7 blockings, when you pass around the sensor 7 times, that is 2 rotation, because you got these 3 different little metal legs sticking out. When it passed through your sensor 7 times, that means you have rotated for 2 complete rounds. So that's 4 pi. So you tell your computer, I'm going to enter 4 times 3.114, the roughly 12 point something. And that is in radians. So if you tell the computer to do it in radians, it will give you an acceleration that's already in the alpha format. And we don't have to divide by R. That's much simpler. But the lab was done intentionally wanting you guys to do it in A and divide by R later, but they made a mistake. But just so happens that mistake was made so that it's very close to 4 pi. So it just so happens now we can still use this data, but simply treat it as an alpha. Okay, I just want to explain why they say there was a arrow, and that doesn't affect your data. Treat it as an alpha, you're still good. They also give you a link for a separate video. And you can ignore that too, because that video is still trying to take data using the circumference, trying to give you linear acceleration. And we are taking it as a angular acceleration. So you can just stick to this video and write down the slope directly as alpha, so the data will still work out. But I do want to point out this little slightly complicated scenario. Okay, so that's all for this particular lab. Are there any questions about how we record data and how we do a calculation? Any confusions?
Professor, for part A, the R that's in meters, is that something we're getting from the video?
Yeah, so what is the radius? Radius, you can see it's that force, that tension is applied through the third wheel. So your radius R is R3. We have read from the video R3 is 30.62 or 26. Yeah, 30.26 millimeters and divided by 2. So 15.13 millimeters is your R3. So you need to divide that by 1,000. That would be in meters.
Okay, thank you.
Sure. Any other questions about this lab? Okay. All right. So if you do have any more questions, if you think of any questions, feel free to email me. And I will see you next week. Bye, everyone.
Thank you, Professor. Have a good day.
Thank you. You too. Have a good day.